The study session ends at 8, right?
No, it actually ends at 7. So it's from 5 to 7 every time.
Thank you.
You're welcome. And you don't have to be there the whole time, but you at least have to be there for, half an hour to an hour to at least gain some information and also to get your extra points. So but yeah, you don't have to get there at 5, you don't have to leave there at 7, but I would encourage you to try to attend. I gave people as much as 10 extra points last week or whenever the last study session was for engaging and participating in the study session. So I don't know if you guys are on the border of bad grades to good grades, you might want to think about doing everything I tell you to do. But anyway, so we're going to start chapter 6, and chapter 6, and I know I say this all the time, but chapter 6 is pretty easy. Once we get to the actual problems, it's pretty simple. It's just that I think, like I told you on Friday, there's a lot of new symbols, there's a lot of new letters. So you guys really have to try to engage with me and stop me if you don't understand, because it's very sort of conceptual at the beginning, but hopefully it'll get easier. I mean, I know it'll get easier because it is really, really easy. So let me start the slideshow. Okay, so I hope you took my advice and you actually read. But if you did read, you would have noticed that the first couple of pages in the book sort of bombards you with like these 4 terms or 3 terms or whatever. And I want to kind of go over them just so that everyone's sort of on the same page. Chapter 6 is thermochemistry, right? So as I mentioned on Friday, there's a whole class on thermodynamics. This is a very complicated subject, but we're scratching the surface here in this class. So it's just kind of to get you acclimated to heat of reactions and enthalpy and all that stuff, but it is really not that difficult. But anyway, so the first word I want to sort of talk about is energy. I think that's one of the first ones they mentioned, but energy, is sort of a word that everyone knows. Like if I say, oh no, I don't have energy to do that, you understand what I mean by that. But it's sort of a very difficult, it's a word that's abstract, right? It's very difficult to define because you can't see it, you can't smell it, you can't touch it, so it's difficult to define. There is a definition for energy. Does anybody know what that definition is?
Is it the ability to like do work?
Right. So it's the ability, that's exactly right, ability or capacity of a system to do work or supply heat. In terms of work, what is work? Does anybody know what work is? That's a physics question. You should know that. Well, work is equal to any force over a distance, right? So how much force do I put from this point to that point? That's what the work that you have to put in. That's what work equals, okay? In chemistry, the primary type of work that we are interested in is called PV work. So we just got off of chapter 5, right? PIVNERD. So PV, pressure, volume. So we're interested in the type of work in PV work, pressure, volume work. As a matter of fact, the concept of work is introduced in order to discuss PV work in the role of the definition of enthalpy. I know you don't understand what that means, but we're going to talk about what enthalpy is. But yeah, energy is the ability or the capacity of a system to do work or supply heat. And what type of work are we mostly interested in? PV work, pressure volume work. So think of like a piston, okay? When you have a piston, the piston can move up and down because of the gas, the pressure, and the volume that's changing in that piston. So that type of work. Okay, so that's the first term, energy. Everybody cool with that? Any questions on energy? Okay.
No.
All right, so heat is the second one. All right, heat is another term which I hear a lot of students always kind of get this not exactly right. So there's in my view, there's a bit of like a miscalculation, a misunderstanding about what heat is. So heat is not, it's not a thing, okay? It's actually just a process, okay? So let that sink in for a second. It's not a thing that you get or touch or whatever. It's a process that's happening. So it's a transfer of energy. We just talked about what energy was, but it's a transfer of energy between two objects that are at different temperatures. Okay, so they heat transfers because objects are at different temperatures. So what gets transferred is the energy, not the heat, because heat is the process of what's happening. Do you understand that? Is everybody cool with that?
Yes.
Okay. The third thing I want to talk about is temperature. Well, that doesn't matter. I was going to say generally we talk about temperature here, absolute temperature in kelvins, but that's not important. What's important is temperature is the property which determines the direction of the process of the heat flow. Okay, so remember, energy is the capacity to do work. Okay, and the work in terms of heat or supply of work or supply of heat, whatever. Well, hold on, I just got an email. Okay, I don't need to know that. So that's what energy is. Heat is the process of that energy transferring from one object to the other. The way that we actually measure that process is with temperature. So temperature is the property which determines the direction of the heat flow when two objects are brought together. So is everybody cool with all of those terms? So the reason I took time to actually define them is because you probably need to know them, right? So you need to understand what those things are. You cannot be confused about them because this whole
Can you
chapter,
repeat the last one, please?
temperature?
Yes.
Yes.
I didn't get the last part.
Yeah, so I mean, these are all in your book, but temperature is basically the property which determines, like, so you use a thermometer to take temperature, right? So the temperature is determines the direction that the heat is flowing when two objects are brought together.
Okay.
Okay. So in this chapter, we're mostly concerned about systems. Okay, so you have to understand what a system is. And a system can be anything you're concentrating on. Okay, so for example, it could be, I think your book gives you, or my video says, it could be your room, for example, is the system, or a coffee cup, or I don't know, your yard, whatever, it doesn't matter. Anything that you're particularly concentrating on is your system. Everything else that's not the system is considered the surroundings. Why do I care to talk about that? Is because you have to understand when we do problems in chapter 6, you have to understand which is heat flowing. Is the heat flowing out of the system or into the system? Because that makes a difference. So you have to define what a system is. In this chapter in chemistry, really, when we talk about a system, we mean a reaction. Okay, so we consider the reaction the system, and everything that's occurring outside of the reaction is the surroundings. Cool? Is that cool with everyone? Because I think I'm going to start then. Yes?
Yes.
Okay. So, since we know what a system is, or we can define it, right? That the system is, let's say, let me show you a particular reaction, right? We have to now classify what type of processes are happening in these systems. Okay, so you have something that is called an exothermic process. Okay, so remember, everything is in the view from the system. The system right now is that reaction that you see on the screen. If that system releases energy into the surroundings, then it's considered an exothermic process, meaning the system starts with a bunch of energy, and then after that reaction happens, it's left with less energy. The actual reaction is left with less energy because it expelled it, it gave it away to the surroundings. If that happens, that's considered an exothermic process. A good example of that is a combustion. A combustion has a lot of internal energy when it reacts, But then when it finally finishes reacting, it releases an exorbitant amount of energy to the surroundings. That is considered an exothermic process. The opposite of that would be a system that takes in energy from the surroundings. So it starts with little energy, and then something happens from the surroundings, like heat or a flame or a spark or something. And then at the end of the reaction, it gained energy, or it gained heat. All right, so that would be called an endothermic process. So exo means out like exoskeleton. So you can maybe help you remember, but exo means going out, and endo means like endothelium, right? Inside. So that means going in. And remember, the only thing you care about is from the viewpoint of the system, basically the reaction. So at the bottom is 2 moles of HGO, right? And that's a solid. For this, and the solid stays as a solid. Nothing happens to the solid. It's stable. It's like a rock, right? Nothing will happen to it unless I or someone comes with energy, like heat or a flame, and tries to melt it. When that happens, then this thing decomposes. So this is an endothermic process because the system is sitting there, and it will stay sitting there until the surrounding does something to it. So at the end of this process, the system has gained energy, and the surroundings has not gained energy, has left, given energy away. So do you guys understand these two concepts?
Yes.
Okay, does everybody else understand besides Justin?
Yes.
Yes.
Okay, because the next slide, you're gonna have to, this is where I'm gonna introduce different variables, okay? And I mean, just try to stay with me because it's not hard, it really isn't. And you're gonna see that when we actually get to the problems, it's gonna be really, really simple. But the first law of thermodynamics, you guys should know what that is, right? What is it? Anybody?
What did you say? I couldn't hear you.
What is the first law of thermodynamics?
Is it the law of conservation energy? Conservation.
Right. What does that mean?
I think it means like whenever like energy disappears, the same amount has to come back or like be resupplied or something.
So energy is not created nor destroyed. That's what the first law of thermodynamics says. All you're doing is repurposing it, kind of like what you said. It has to come up somewhere else, right? So we can't create, no, there's a constant amount of energy in this world. And the only thing we're doing is we're changing the form of it, okay? It's either from heat to a gas, or, that's why this whole, that's why we have reactions. That's why we balance reactions, because we can't make up stuff, right? It went somewhere. Someone took it. If someone doesn't have it anymore, it's because it was given away. It's not that it just goes away and it poofs, goes away, it disappears. That's the first law of thermodynamics tells you that there's no energy created nor destroyed. It is just changed into different forms, okay? So knowing that, again, the first law of thermodynamics is the application of the conservation of energy principles to heat and thermodynamic processes, okay? So the first law, and this is what it is for chemistry, this is how we write it, right? So the first law makes use of internal energy. Internal energy is the U, okay? That's the symbol for internal energy. Makes use of the internal energy, heat, and the work of a system. So Q is the symbol for heat. You need to know that because we're going to play with that a lot. W is the symbol for work. Work actually stands for PV work, which I talked about before, right? So the definition of work as an equation is work is equal to the negative of pressure volume, of pressure times volume. So when I'm talking about work in chemistry in this chapter, I'm referring to pressure volume work, okay? So in layman's terms, if I want to find out the energy of something, I would have to add up how much heat it takes in or it gives out, and I would have to add that to how much work is being given to the system or taken out of the system. That's how I figure out how much energy the whole complete system has. That should make sense. Okay, so is everybody cool with that? Okay. In this chapter, and I keep saying that because it's very different in other physics and other scenarios, but in chemistry, we literally are just concentrated. All we want to know is how much heat is being transferred into or out of a system. Remember, systems are reactions. So I want to know, if I do this reaction, I want to measure how much heat is leaving this reaction or going into this reaction for this thing to actually happen. That is all I care about in chemistry as far as thermodynamics is concerned. Okay? Is everybody cool with that?
Yes.
Okay. The easy part about what we're doing also is that I would like to know the heat that flows into or out of a system at constant pressure. So there's different types of experiments, right? I can do experiments under constant volume, and if you looked at your chapter, you should have noticed that there's a whole section that says constant volume calculations, heat transfer under constant volume. You don't have to worry about that. Let me say that one more time. You can skip that entire section on constant volume. You do not have to do any problems on that. All I want you to concentrate on, the only thing I want you to concentrate on is heat transfer of systems, right? The heat transfer of a system under constant pressure. First of all, it's a lot easier. We can assume a bunch of stuff, and the calculations are way, way easier for you to do. So when you do this, when you do a reaction under constant pressure, and think about it, constant pressure is very easy because we're under constant pressure right now. You live under the same pressure, right? We're at 1 atm. If you're by sea level, we're at 1 atm. It's not like we're not going up and down in an airplane every 5 seconds. So constant pressure is very easy to do because that's what we normally are at. Think about what it would take to do a constant volume type of experiment, right? That's very difficult. You have to have something they're called bomb calorimeters. And it's very technical what the type of experiment that you're doing versus a under constant pressure type of experiment. But anyway, if we're doing things under constant pressure, we have to change the first law, the way that it looks a little bit, because this is the first law of thermodynamics, very general. It's a very general way of saying the first law of thermodynamics. Energy is not created nor destroyed. And if I wanted to find the energy of something, I would take how much heat is expelled and add it to how much work I have to put into it or take out of it. That's basically what that equation says. Okay, but if I want to do something under constant pressure, I got to denote it. At constant pressure, the symbol of Q changes. Okay, so the symbol of Q now becomes delta H. So this right here, enthalpy, is the same thing as heat. Same, right? So you know what heat is, we talked about it, right? It's the process. It's the process of energy going into or out of a system. So that's the symbol Q. But when you do experiments under constant pressure, now you don't call it Q anymore. Now you call it H. And H stands for enthalpy. So what is the definition of enthalpy? The heat flow into or out of a system under constant pressure. What is the definition of heat? The heat flow of a system going into or out of a system. So the only thing that we're adding here is that it's under constant pressure. Is everybody still with me?
Yes.
Okay. So when we talk about experiments under constant pressure, we have to also define what is work. And I said it before, work is equal to negative P delta V. So PV work, pressure volume work. So when we do a problem, I'm going to erase this. When we do a problem under constant pressure, we change, like I said, the Q to delta H, and now we call it enthalpy. The work, we just substitute what work really is, which is pressure volume, okay? And we substitute it, now it looks like this. So the Q became H, the work became P delta V. And since my goal in chemistry as a chemist is to basically just figure out how much heat enters or leaves a reaction, I'm going to manipulate or rearrange this equation to solve for H, because that's all I care about is the heat. So if I do that, then it becomes this, all right? It's the same law of thermodynamics. It is just that I have rearranged it so that it's under constant pressure, because I know that, because it's H instead of Q. And I've rearranged it so I can solve for heat, not energy, like the first original law. Is everybody still with me? Because that's pretty much it. I do have a couple things I want to say but that this is pretty much the concept of enthalpy and how it relates to the first law of thermodynamics and what we're interested in as chemists. Yes?
Yes.
Okay. So enthalpy is a state function. Can anybody tell me, does anybody know what that is? What is a state function? I mean, if you read, it was on the first page. So this is really telling. If nobody can tell me what a state function is. Hello, anybody? Okay. State functions, like on the first page of your freaking chapter, are those functions that do not matter how many steps it takes to complete it. In the first page of your chapter, it shows a dude going up a mountain. And the dude either takes a straight line from the bottom of the mountain to the top of the mountain, or takes a really curvy freaking way to get to the top. But the beginning, both dudes start at the same spot and they end up at the same spot. The concept of state function is that it does not matter the path that I take, I will start at the same spot and I will end up at the same spot. If I do that, then that's considered, and well, hold on. Yeah, a state function tells you that it does not matter what path you take, it just matters where you begin and where you start. Enthalpy is a state function. So let me put this to you in chemistry terms. Let's say I have a reaction that shows you the reactants and then gives you products. But that is like the beginning and the end. But that reaction, that could be the summary of the reactions. Let's say that to get to those products, you actually have to do like a bunch of several steps to get to that product. That doesn't matter. All I care about is finding out how much heat the products have and minusing it, right? Subtracting it from how much heat the reactants had. So it doesn't matter that the process actually went through 17 steps. I don't care about that. All I care about is where you ended and where you started. That is a state function. And it's good news that enthalpy is a state function because it is, we can do certain calculations that we're going to do at the end of the at the end of the class. For example, Hess's law is basically considered this, basically bases his law on the fact that enthalpy is a state function. There are other variables that are state functions. For example, pressure is a state function. It doesn't matter if in an experiment you've got 17 different pressures that the thing goes through. What's the end pressure and what's the beginning pressure? That's all you need to know. So pressure is a state function, volume is a state function, and enthalpy is a state function. Okay? So you do need to know that. Do you have any questions on that?
No.
Okay. Another thing that you guys need to know is that Q, heat, and W, and energy, or heat, enthalpy, sorry. Yeah, enthalpy, Q, and W have a sign convention. All right, so let me, ooh, somebody's alarm. So what I mean by that is, oh, I just realized that I'm not on the camera. Anyway, what I mean by that is that I think your book talks about it in terms of a bank account, right? So for example, your system is a reaction, right? It's a combustion. The system, the reaction, is going to expel, give out a bunch of energy after that reaction is done. So it's going to give a bunch of energy to the surroundings. So that means that when the system before it reacted, it had a bunch of energy to start with. But at the end of the reaction, it gave away a bunch of energy. So there's a sign convention. So the amount of heat that it gave off to the surroundings now tells you that it should have a negative sign. If instead the system takes in energy, right, the sign of the energy would be positive, because it started with less energy, but the surroundings gave it energy, so therefore it ended up with more energy. So it has a positive sign of energy. So that concept of putting signs, negative or positive, that is very important, because you need to know that when they're giving you word problems, they're going to tell you, okay, so the system let go of blah, blah, blah. They're not going to tell you put a negative sign. You have to know that. So there's a sign convention for enthalpy, there's a sign convention for heat, and there's a sign convention for work. The same concept. If the system does work, actually does the work, then the system is going to have a negative sign in front of that number, right? Because all this is to calculate numbers, to calculate values. But these values are going to have a negative number or a positive number, depending on which way the thing is flowing. And you need to understand that. I think your book talks about it in terms of a bank account, right? So if you start out with $100 and you gave away $50, you have minus 50, right? So because you gave away 50, it's sort of like that. Okay, so you need to be able to understand that to do these problems. Does everybody understand? Did you get that? Do you understand that?
I'm a little confused.
Okay, about what?
So you said that if the system gives off energy and it still have a negative sign.
Correct.
So
Not
like,
that's exactly what it is. It's a negative.
Is that like related to the endothermic and the exothermic processes?
Yes, absolutely. So an exothermic process, in terms of the system, from the system's view, an exothermic process means that the system gave away energy to the surroundings. So therefore, an exothermic process will always have a negative H value, a negative heat value, because it gave it away. And I do, before any other questions come up, I do want to make a point. These sign conventions are basically for us humans to understand the direction that it's happening, right? Because there's no, if I ask you, if you tell me that the answer to this question is negative 35 enthalpy. So basically saying negative 35 joules of heat were expelled. That doesn't make sense, right? Because there's no negative heat. That doesn't make sense. There is no negative work. What? How can you do negative work? You either do zero or you do work, right? But this convention, the whole sign thing is for us, it's for humans to understand which direction it's going. Did it go out of the system or did it go into the system? That's what the minus and the plus does. So hopefully that makes it a little bit more palatable to understand. Do you understand, Camille?
and you just put like in the corner, like of it. Did you
What
hear
do
me?
Sorry, I couldn't hear you. Say that again.
Like where would you put the sign at? Like,
Okay, so you'll see we're doing it, but we literally put delta H, right? Because that's what we're solving for, heat, the heat under constant pressure, and you'll put a negative number. So the negative goes in front of the digit.
okay.
Yeah. I mean, the answer is either negative or positive, right? So that's where you would put in. I'm going to show you that right now. But those sign conventions are important because, again, the problem is not going to tell you put a negative sign. No, it's going to say it's an exothermic process. So you need to know, oh, exo. So that means it's negative. Endothermic, oh, that's endo. So that means it's a positive value, a positive enthalpy value. All right. Okay. So enthalpy, any other questions? Sorry. Any other questions besides Camille? All right. So enthalpy, again, is used to, all it does, it tells you how much heat flows into or out of a system under constant pressure. That is the key, all right? Because if it wasn't under constant pressure, then we wouldn't use H. We would use that symbol Q, okay? So under constant pressure, heat flow into or out of a system is H. It is a state function. I mentioned that. So it doesn't matter how many steps the reaction takes. All that matters is what products you get and where you started from. So that's why this delta H right here, that means the change in H. So all you would do to literally find the answer that we're gonna do these problems, all you gotta do is you would add up all of the enthalpy values of the products and subtract it from the enthalpy values of the reactants. That's what a state function allows you to do. You can do the same thing for pressure. What was the other one? Volume, internal energy. You can do all that for any state function. All you need to do to find the value that they're looking for is take whatever the end is minus how it started. So anyway, yes, I already said that. Okay, so this is in your book, right? This is in your book, but the way you read it is on the left-hand side. This is just another way of telling you what I just mentioned. On the left-hand side, you're looking, the reaction starts here and it's going down this way, right? So this is, look what it is, it's a combustion. A combustion is an exothermic process. It gives out a bunch of energy to the surroundings. And here's the enthalpy. It tells you exactly how much energy it gives off in the form of heat, right? So we measure, right? So what happened is that 890 joules left the system, the reaction, and went to the surroundings, which is why it has a negative sign. So that is how you would define negative or positive in endo or exo, all right? So on the opposite side of that, you would have an endothermic process. So here you have ice, right? Water solid, and what ice will stay ice unless you do something to it, right? You have to, if you were to try to heat it, if you heat a piece of ice, so that means that the surroundings is actually putting energy to the system, and what happens, it turns into liquid, but look at the enthalpy value. It's a positive number. Why? Because the system took in energy from the surroundings. And how you know that is because it's a positive number. All right, so does that make sense to everybody a little bit more?
Yes.
Yes.
Okay, so that's literally it as far as the concept behind it. Well, we haven't done calorimetry yet, but the basic fundamental of what we're trying to do, right? In this chapter, all we're trying to do is measure the heat of reactions. That's it. But to do that, you got to understand why, how do all these things relate? So how does the first law of energy of thermodynamics relate to all of this? And you got to know that when we do it under constant pressure, we change the value. We change the symbol to H instead of Q. We're going to use Q later on, but when we're finding enthalpy, right, heat flow under constant pressure, we need to do it with H, all right? And I can go into more detail as to why delta H equals Q, but seriously, you don't need to know that to do these problems, all right? So that's what you need to know. Now, when we're actually, before we do the problems, you need to know a little bit of bookkeeping things, right? Because these problems are gonna be, they're gonna be given to you, and you gotta know, like, okay, well, what happens if there's stoichiometric coefficients? Right? Like, I'm going to give you a reaction, and does the 2 in front of the water, does that mean anything? You need to know that. All right, so that's what we're going to talk about now. So this stuff is really easy from now on, hopefully. Okay, so if you have, for example, something going from solid to liquid, right? Well, let me read. The stoichiometric coefficients always refer to the number of moles of a substance, sorry. So if you go from solid to liquid, right, and that is an endothermic process, you know that because obviously the number is positive. But what happens if now you flip that reaction? If instead of going from solid to liquid, you flip it, you go from liquid to solid. What do you think happens to this number?
It goes to -6.
Exactly. It flips. Exactly. If this way is, solid to liquid is endothermic, then liquid to solid must be the opposite, must be exothermic, which is exactly what happens. It's the same number, you just change the sign. And this is what I want to show you. Like, there is no such thing as negative energy, negative heat, right? That's what it's saying. It's saying that the heat flow was negative. That doesn't make sense. That doesn't exist. But it tells us which direction it's going, which is important for us, okay? So if you ever flip a reaction, which we will be doing that, all right? If you ever flip the reaction, then you must remember to flip that number, right? To flip the sign. Okay, now what happens if instead, here we had 1 mole and it was 6, right? So if I instead have 2 moles of water, 1 mole of water is 6, 2 moles of water would be 2 times 6, right? So the coefficients matter is the point here. So once you figure out what the enthalpy value is for 1 mole, then let's say you have to balance the reaction or do something to it, and you change that coefficient, you got to change the number accordingly, the enthalpy value accordingly, okay? So everyone got that?
Yes.
So another thing is states matter, right? So the physical states of compounds, substances matter. So for example, if I'm going from solid to liquid, which you've already seen, is endothermic. Do you think going from solid to gas, or going from liquid to gas, do you think it's going to be the same number? Yes or no? No, right? Do you think it's going to be more, or do you think it's going to be less? Sorry, I have to close my... Do you think it's going to be more, or do you think it's going to be less?
It's going to be more because it has a greater specific heat.
That's right. It's going to be more because it takes more energy. It takes less energy to melt something. When you melt something, okay, yeah, it takes energy. But when you vaporize something, it takes even more energy, right? So that number is going to be different, right? So the point here is that states matter. You're going to have an appendix. We're going to talk about that appendix, but there's an appendix in the back of your book, which has a bunch of enthalpy values, right? And you're going to have to use the appendix to look stuff up when you're doing problems. But when you look them up, you have to look for exactly the right one, because water solid does not have the same value as water liquid or water gas. Okay, so you have to make sure that you're looking for the right one. So that's the point of this, is that states matter. Okay, and then what else? Last thing, and then we'll do problems, because what time is it? Yeah, okay. So it says here, there's no way to measure the absolute value of the enthalpy of a substance. Okay, what does that mean? So I gave an example, same problems that geographers have. So geographers, what do? They measure the altitude of things, right? They measure how the terrain is and blah, 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 blah. But one of the things that they do is they measure the altitude of mountains, of whatever. So when you measure a mountain, where is that measurement taken from? Like, what's the base? Where's the base taken from? Where you're standing?
Sea level?
Sea level, right? So basically like where you're standing, like where the floor is. So is that where, and this is the question now, is that where the mountain actually starts?
No, it's on the tectonic plates somewhere in the ocean.
Exactly. Somewhere in the core of our Earth that we can't get to, right? So that's a problem. That's a problem for geographers. But what do? They say, nah, screw it. We're gonna take a baseline here, and the baseline is gonna be exactly what Justin said. It's gonna be at sea level. So that is our zero, okay? But that's not exactly correct, but everyone accepts it because that's basically what we can do. The same concept happens for enthalpy values, enthalpy of formation values. So for example, oxygen, right? Oxygen, when we talk about oxygen gas or oxygen, we talk about oxygen in general, we know that oxygen exists naturally as O2, right? We don't see O by itself if we were to take a sample of air. It doesn't occur that way. It occurs as O2, but it naturally comes that way. And right now, unfortunately, we don't have the technology to actually measure precisely the internal energy that it takes to form something that already naturally comes that way. So what do? We take a baseline. We say, screw it. If it comes like that naturally, we're just gonna basically assign it a value of 0. Do you remember oxidation states? Remember what we did with oxidation states? And that wherever something was naturally that way, like magnesium solid, we would put a 0. That's the same thing that we're doing here, okay? So there's certain values that you just have to know, right? So if something comes naturally, like in a reaction, if I have magnesium solid and we need to find the enthalpy value of whatever, you need to apply a 0 to magnesium solid because that's the way magnesium typically comes. Everybody else you don't have to remember, but like those you have to remember. All right, so what does this say? This here is another variable, but it's the same. Let me explain to you. So this is delta H, right? Same delta H that we've been talking about. The little f stands for formation. The little 0 at the top means standard, right? So the standard enthalpy of formation. What does that mean? How much energy, how much heat does it take to form this compound at standard pressure? That's it. That's all it means. But that's the little symbol that we use. So again, these are the values that you're going to find in the appendix. How much energy does it take to form this compound? You would look up that compound in the appendix. Some of those compounds are going to have a value of 0 because of what we just talked about. But for example, if I was to look up O2, like I just said, you would see that in the appendix, it's 0. Now, if I wanted to look up the standard enthalpy of formation, so how much heat it takes to form O3, it would not be 0. It would be a value, which that's what it is. Okay, so that's what this is. The standard enthalpy of formation means how much energy does it take to form this particular compound. That's it. Another example is graphite, carbon. So carbon naturally comes as graphite. So when you look it up, and you look this up specifically in the appendix, you're gonna see 0. But diamond is not a natural form of carbon. It actually takes energy to form diamond, the allotrope, right? So you would see a value for it. So are you guys okay with this? You guys cool with this? Because we're gonna start doing problems very, very soon. Not the next slide, but the slide after.
What did you
Yes.
say the 0 stands for?
I'm sorry?
The 0, you said the F stands for formation. What does the 0 stand for?
Standard.
Standard.
Right, so at standard temperature, standard pressure, sorry. Standard enthalpy of formation is basically the heat that it takes to form that compound at standard pressure. That's what it is. Right here, yeah, I got pressure of 1 atm. Okay, oh, this is a little snippet. This is not the whole appendix. The appendix is like 5 pages long, but this is a little snippet in the chapter. So if you notice here, look at nitrogen gas, right? Nitrogen gas comes naturally as N2. Look at the value, it's 0, right? But then if you look for something like aluminum, right? Aluminum solid, that comes as a solid, it's usually 0. But everybody else has a value because that's not, you react it to get that. So, and then obviously you see that they all have different states, right? Gas, solid, liquids. When you look at the appendix, you gotta look for the correct specific one. Okay, so now the next slide Okay, so take a breath because this is really easy. It's just that I'm gonna freaking put this on here and you're gonna have a heart attack. Okay, so remember the point that chemists want to do for this chapter. The point is I want to figure out how much heat, and don't get freaked out by this equation, but all I want to do is figure out how much heat this reaction takes in or gives off. That's all I want, okay? So what it's telling you, this is the slide for Hess's law. Remember that I said that enthalpy is a state function. So therefore, all I have to do is add up the enthalpy values of the products and subtract them from the enthalpy values of the reactants. That's all we're doing. So if I had a theoretical equation or theoretical reaction with A and B reactants yielding C and D products, to find how much heat is being expelled or taken in by this reaction, I would take the sum of the products. See how this is C, right? C and D. I would take, and this is the enthalpy value of formation. So I would take, go to the appendix, find the enthalpy values of all of the products, add them up, and then subtract it by the enthalpy values of the reactants. That would give me the answer. That's all this is saying. Okay, this little c here corresponds to the little c here, which means if you have a mole of a coefficient, right? So if you have 2 moles of C, you would multiply whatever the enthalpy value is times 2. That's all it's saying. So basically, Hess's law tells you that if you take the sum of the products and you subtract it by the sum of the reactants, you get the enthalpy value for the reaction. That's it. That's why the fact that this is a state function is really, really helpful. Because if we didn't have this, then we would have to individually go through all of the steps of all of the reactions and, add them all up or whatever. We don't have to do that. All we got to do is take products minus reactants. We're done. Do you guys have any questions on this?
No.
I do.
All right.
Okay, so can you say one more time how the smaller C or D or A or B corresponds to like the entire thing of what it has to do with it?
So for example, let's say that this was O2. Okay. This was O2. And this was O2 and I don't know, water, whatever. To find the enthalpy of reaction, I got to take the enthalpy values of the products and subtract them from the reactants. So the enthalpy value, I would go to the appendix and look for O2. I know the O2 should be 0 because it comes naturally as O2. The little c, let's say there was 2 moles of O2. I would put 2 times 0 and I would add it to whatever water is. Let's say I had 4 moles of water. Then I would add the little d, means that's what the little d is, right? Little d, right? So 4 times whatever water is, which I think is like, I don't know, negative 285 or something like that. This is a value that I know it because I just did it in the other section, but you would look this up. And then that would be the sum of the products. And then you would do the same thing and do the sum of the reactants and then get your answer. That's it.
Okay, I get it. Thank you.
Yeah, no problem. It's really, really easy. Like it really is. All we're doing is taking products minus reactants and getting an answer. That's it. And that is Hess's law. Hess's law says that whenever reactants are converted to products, the change in enthalpy is the same whether it happens in one step or in many steps. Okay? And yes, I already told you that enthalpy is a state function. Okay, so let's do a problem. Let's do it because it's really easy. So I need you guys to practice looking at the appendix because you're going to need to know how to look them up. So you got to tell me, someone help me do part A. I want to find it's appendix 3, by the way. I want to find the enthalpy of reaction for that part A. So what do I do? What's the general equation that we just talked about?
It was Hess's law, right?
Right, which says what?
It takes the sum of the products, minus the reactants.
That's it. That's exactly what it is. Sum of the products minus the sum of the reactants. Okay, so let's do A. So tell me what to write. So I would write delta H of reaction, right, is equal to what?
Two times the enthalpy of formation for hydrogen gas.
Nope. What goes first, Justin?
Oh, I was doing it with the other way with the sign and backwards, but you'll put the products first.
That's right. So 2 times what? The enthalpy value of who?
The hydrogen monoxide.
Yes. So someone needs to tell me what the value of water is. And we don't have that much time. We have 3 minutes, so you guys better hurry up and use your appendix or find it, because I am not going to move on until somebody engages with me.
Negative 285.8.
Okay, so tell me what to write now completely.
Do 2 times, 2 times 0, right? Because,
What goes first, you guys? Isn't it product?
yeah, 2 times 0. Wait. Oh, wait. I'm still confused. I'm confused. Why wouldn't we do 2 times H2?
Because we're doing products minus reactants. Products minus reactants, right? Because it's a state function. So when you do that, the change in H, right, means H2 minus H1. So H2 is products, right? So you got to do the products first.
It would be 2 times negative 285.8 kilojoules per mole.
Right, and that's what they all are, so I'm not going to rewrite it all the time, but negative 285.8, okay.
Minus.
Minus.
And then you would have parentheses or brackets, depending on how you want to write it. And then you would add the enthalpies of formation for the two gases, but since those are how those gases come, they'll both be 0.
Yes, so you would have 2, you got to write it all, Justin, for the class, because so that they understand. 2 times 0, because there's a 2 here, and this would be 0, and this would be 0. So 2 times 0 plus 0, there's no coefficient. You would close the parenthesis, the bracket, and that's it. That would be the answer. So the answer is basically 2 times negative 285. Is it exothermic or is it endothermic?
It's exothermic because from the point of the system, it loses energy, which means that it gives it to the surroundings.
Correct, because of this negative right here. That's what makes it exothermic. So what is the actual answer? Negative, what, 400 and something? Or no, more. 570 something.
Negative 571.6.
Okay, that would be kilojoules per mole, okay? This is how you do these problems. It's literally this simple. I want to do part B, but it's already 4:31. So we'll start from part B tomorrow or whatever, Wednesday, you know what I mean. But it literally, all we're doing is products minus reactants. It's not reactants minus products, right? Products, whatever you result is minus what you started with. That's what a state function is defined as. So practice this because on Wednesday, we're going to do this, obviously part B, and then we got to do this. This method that we're doing right now is the easy method. It's called the direct method. Why is it called direct? Because you directly use the enthalpy values in the appendix, right? This is easy. I just look them up, take products minus reactants. The indirect method is a little bit different. You have to use the equations. You don't use an appendix, okay? You got to use the equations to get the answer. So we got to do that. And then after that, we got to talk about heat capacity, calorimetry, and then we got to do problems on that. So heat capacity and calorimetry, you're not going to really like a lot. I love them, but you're not going to really like a lot. So you have to practice this and not wait till Friday, right? Because your exam's on Monday. So you really do need to practice this now. And the fact that a lot of you couldn't tell me what a state function was means that you didn't read. So I don't know if you understand, but your exam is on Monday, this Monday, coming up. Okay. So any questions? If there are no more questions, that you are more than welcome to leave. That's it. I will see you on Wednesday. Remember that there's a study session today, please.
Thank you. Good day.
Thank you guys. You too. Hi, Kezia.
Hi, did you get my email?
Yeah, I answered you. And you didn't answer me back. So.
Oh, is it okay if we talk about it now?
I have, hold on, let me just make sure. I can't talk about it for too long. I have a meeting at 5, but if it's quick, I can try. Let me stop recording. Hold on, sorry.